Hi, Hasan, you're live.
Everyone who is here. Thanks for taking out the time to attend the DSC conference. And thank you, especially Amelia, for organizing this and inviting all the industry experts here for us to gather here and share our knowledge. All right. So before I begin, I would just like to interact with everyone here. I already see 735 people here. So before I start, just wanted to have a thumbs up on how many people are here who actually belong to the industry. That, like I was told earlier, that most of the people will be from the data science industry, and so I've prepared accordingly. So I have about my workshop, you might already be knowing that it's anomaly detection in time series. So I just wanted to have a quick overview of what my audience is right now. So how many of us here are do actually go to college, or let's say are graduating right now, starting their first jobs, let's say, or maybe in their very initial career? How many of us of the 736 that I see right now here, how many of us are in their very initial career, I would say? Any thumbs up? Any comments? DS. You are a data scientist. Awesome, Bilal. Awesome. Okay. So let me start by sharing my screen. Oh, awesome, awesome, awesome. Okay. Okay. Hi, Robert. Hi, Ratu. Third year, Abid Hasan. Okay. So I see there's a mix of you. DS student. All right. So I guess today's workshop is basically aligned towards everyone who is here. We'll see some really unique methods and some really, I would say, intuitive methods how we can analyze, and how probably a lot of you might not have thought about time series from a different perspective. Let's say. Thank you. Thanks, Thomas. Okay. So let me, it's totally fine if you're a beginner. It's absolutely fine. Everything that I'll be covering today would be, I would say, just elementary mathematics and your intuition and your pattern matching, let's say, just general knowledge, I would say. But it will give you a sneak peek how you can maybe change your view into the time series, or let's say signal data. So I think let's start the presentation, and the rest conversation we can make in between my workshop. All right. So allow me to share my screen, and I'm really new to Crowdcast, so just bear with me for a moment. Okay, I've shared my entire screen, and okay. I guess the only challenge would be that while I am presenting, I won't be able to answer your chat or maybe interact with you. And that I think is really a problem. So meanwhile, what I'll do is I'll just get back to chats and talk to you guys. Right. Okay. Awesome. So anomaly detection in time series, as you all know. So anomaly is actually something that we find a different from the normal data. A unique pattern, or you can say a different value in normal data. So about me, I am Hasan Ali. I'm a deep learning researcher at pulpvision.ai. And pulpvision.ai is basically a deep tech AI startup which solves, which basically builds AI products and solutions for different industries and enterprises. So these enterprises could belong to any particular sector. Let's say it could be oil and gas. So we have worked for oil and gas in the past. We have worked for e-commerce in the past. We have also worked for agri-tech, satellite imagery, and a lot of other sectors basically. We major in, or our experience is basically in computer vision and very less of NLP. But today this talk is more or less about time series analysis, or what we can also say is finding anomalies in time series. So let's start with it. So what is time series? For people who, let's say, are managers or work in very high extensions of organizations and have very less idea, let's say, what is time series. So from a very layman point of view, a time series is just a data which can be represented in the form of time. So for example, if we are measuring a temperature of a city for the continuous last 30 days or 60 days or 90 days, and if we are plotting that data on the graph, it is simply a time series data. So it is a time series data is also I would say, it could be discrete in a way, or it could be continuous as well. So for example, the sensors. So let's say we have temperature catching sensors, which are catching temperature for the continuous 30 days. That could be a continuous data and time bound. So for example, what is the temperature today? What is the temperature yesterday? A time series data could also be sales of a company in the last year, or from the past 3 consecutive years, what is the sales of a company? And if we plot those sales with respect to what is the sale every month, if you plot that data with x-axis as the year and y-axis as the value of the sales, we would get a time series data. So anything which is time based is actually time series data. Sorry. So in this example also, as you see, let me have a pointer here. Okay. So in the x-axis, there is timestamp, and on the y-axis, there is some value. So as time is increasing, how the value is changing, that is basically represented by a time series, right? And a very famous example is trading data, like all the stocks and very famous topic of cryptocurrencies. Basically, all this is basically time series data. Now, what is an anomaly in time series data? So whenever there is I would say that in almost every data that is there in our universe, or at least known to man, there is some pattern that is conserved. Whether it's rotation of Earth or revolution of Earth, whether it is the Halley's Comet, whether it is the meteorite, everything has a particular pattern. So Earth takes 24 hours to rotate on itself, a continuous pattern. It takes 365 and 1/4 days to revolve around the sun, a pattern again. So I would say there is a pattern in everything. In fact, in our lives, there is a pattern. In fact, in we take birth and we die eventually, and that happens with every living organism, and that is also a pattern, right? So I would say in day-to-day life, everything that you can think of, there is a pattern in electricity consumption, in your daily regular activities, in a company, your daily 9 to 5 schedule, everything is basically a pattern, right? And anomaly is basically just a different day from a usual pattern, right? So let's say someday a different thing happened. For example, let's say, unfortunately, let's say someday tsunami happened, right? And that would be an anomaly. A break from a normal day is just an anomaly, right? And in time series analysis, or in say in any sector, whenever we talk about, let's say, banking, or let's we talk about signal processing, signal from electronics or any devices, anomaly detection is one of the most important aspects, or one of the most important applications, I would say, of time series. And it's very important to detect all these kind of anomalies in the data. It's very important. It's one of the most critical and crucial tasks to first of all and first hand detect the anomalies in the data. So I hope so far it is clear everything. I'll come back to the chat again. Ask question feature to get your question answered and upload. Okay, so I think I hope I'm audible, right? Give me a yes if I'm still going for me. Yes. Okay, awesome. So I think I am audible to everyone. And if you guys have any questions so far, let me know. Any questions? Or we are good? All right. Awesome. Okay, awesome. Thank you guys. All right. So I have to kind of break this presentation feed and come back to our actual chat back to back again, so that I can answer if you have any questions, right? Now let's come to the methods of detecting anomalies. And these are very, I would say, very basic methods that anybody could understand when I will explain, right? So method for detecting anomalies. So first is analyzing the data, which we'll discuss what is, then finding central tendencies and using those central tendencies to identifying the anomalies. Then there is clustering, again, very popular and an important approach. Then there is autoencoders. Now, autoencoders is like the state of the art in this particular setting of detecting anomalies. State of the art, I mean, they are like the most advanced methods of detecting anomalies in time series analysis, and they are based on deep learning, which is neural networks basically. And we will also discuss and dig very we'll not go into very much detail of how autoencoders work, but I'll be able to explain you how we can use those to detect the anomalies. So let's start. Now, analyzing data. So first step of detecting the anomalies are analyzing the data. So one can easily analyze the data like manually or by visualization and detect the anomaly. So for example, in this chart, you can see we can easily, so this data is basically of energy consumption. So on the x-axis, you see number of hours. On the y-axis, you see energy consumption. So there is a normal pattern that is being followed until you see an anomaly here. There is a sudden rise in the in the consumption, right? So basically, this is known as an anomaly. And this we have understood just by visualizing. We have just plotted this data and we have visualized this and we have detected that here we have an anomaly. Now, here we just have data for 96 hours for 4 consecutive days, 96 hours. In industry, we usually have data of billions of hours, right? We have data of years, right? If that's the case, that we have data of years, we would have a million data points here, and as a human we cannot analyze where the anomaly is, right? So these methods are very naive in a way of manually analyzing and probably are not used in the industry, but it's a good way. So every day or someday or the other, you'd have to kind of take a particular piece of that time series, extract it, and then just study it, just to kind of get more insight into the data. So that we would, as a data scientist, anybody could do, and I guess most people do, but that still does not help us in a way because we cannot grasp the entirety of it, right? So this is a very naive method of visualizing the data and finding the anomalies, and it is normally done for very small data. And in industry, nothing, there is nothing known as very small data. Now let's come to the second part of it, which is basically finding central tendencies. Now central tendencies are basically the mean, median, and mode of the data. And let's say in this example, this is on the x-axis, we have sample number, which is just any number, and on the y-axis, we have voltage. Now let's say we have 2 different data samples, the blue one and the red one. And these lines, if you notice, now if this is the data, and let's say if we want to find out the mean of this data, for the blue one I'm saying, if we have to find the mean of this data, I think you would agree with me if I say that the mean would pass through 1.2. Y is equal to 1.2 would be the mean of this, right? And this upper bound and this lower bound would basically behave as a standard deviation, plus minus 2 standard deviation below the mean, and let's say plus 2 standard deviation above and minus 2 standard deviation below the mean, right? And if you remember, there is this method of box plot wherein you take the IQR. So let's not go very technical into the details of what box plot is, but to a layman, how we can detect the anomalies from this data. If let's say you consider plus standard deviations above and minus 3 standard deviations below the mean, I think any data which is above 3 standard deviation and below the standard deviation, if it is normally distributed data, I guess we can call it an anomaly. But the problem with this case is not all data is normally distributed. And I have never seen a data set which is normally distributed. I mean, imperfections are around us everywhere, and hardly you would see any normally distributed data, whether it could be the income of a nation. As you already know, income of a nation is always skewed, right? In industry, you would normally never find a column which is normally distributed, and this method fails if we, let's say, apply it on a data set which is not normal. So far any doubts you guys have? So far any doubts? I've come back to the chat to ask. You can ask me if you have any question. I guess it would your questions would come here, I guess. All right. Okay. Awesome. So I hope I'm clear till now. So I'll proceed. Okay. So this is finding central tendencies. Now next is clustering. So I'll tell you this example from an e-commerce perspective. Now, in an e-commerce industry, let's say we are selling chocolates, and this is actual data from one of my clients. I cannot reveal the name, but this is actually a chocolate brand, right? And I think a lot of you might also guess from the names that I've written there. But the point is, let's say we have a chocolate, and the chocolate comes in multiple packets. There is a 5-gram packet, there is a 10-gram packet, there is a 15-gram packet, there's a 20-gram packet. So in multiple packets, right? And there are different buyers for each of these different packets of the same chocolate, basically, right? But if we, let's say, plot the data of the selling pattern, so if you notice, this is on the x-axis I have plotted the month, and on the y-axis I have plotted basically, let's say, the sales. How many sales for every month for each of these products? And these are all these products whose sale is there, right? If you notice, all these are very similar patterns. Like almost all of them had the most sales in this month, and whenever either of them had a peak in their sales, the other ones also had a peak in their sales. What I mean is, these all these products are very highly correlated. They have a very high similarity. Do you agree with me that these guys are, all these patterns are very highly similar? Yep. Are they similar? Like very highly correlated? That is seasonality, but it might be seasonality for some products rather than the other. So for example, some products are seasonal in some time and the other products are seasonal in some other time, basically. So basically we can, so when we, let's say, we want to forecast for these products, we can cluster them together, and then we can, so the pattern would be the same for all these products. Only the multiplication factor would be less or more. So yes, this is seasonality, but I would say there's a very high correlation between all these products because they are very similar to each other. And being seasonal and being correlated just makes sense and basically agrees to the nature of that product, right? So if, let's say, we have to find an anomaly in this particular setting, right, what we can do, so that's the thing. Let's say we are finding an anomaly in a setting wherein the data is not correlated, or there is no such kind of correlations in the data, some kind of patterns is not there. Let's say when one product sale is increasing, the other one product sale is decreasing, right? And let's even say for a single product, if we have just sales for a single product, let's say a purple one, how can we say that this data point is actually not an anomaly or basic, or this could be an anomaly? How can we say if this point is here an anomaly or not? So clustering is actually not so successful in detecting anomalies, but it sometimes is used. But it would, whenever clustering is used, it totally depends upon the data. If data does not has that amount of randomness or variation, then we cannot use clustering. So clustering has a very limited approach, I would say, and a very limited horizon to application on how many applications can be used. There's a very limited horizon to it because it usually fails wherein there is a very random pattern of anomalies, and anomalies can happen anyway. Like it could be above the line, it could be also below the line if, let's say, the data is incorrect, right? So clustering, we use clustering a lot of times, but the application of clustering is limited. That's the point I'm trying to make, right? Right. Okay, awesome. So the next method is, and I'm sure there are many other methods. There are infinite and numerous methods which we can use for anomaly detection, but these are some of the major ones. But what I can assure is what we are going to study today, which is one unique method which can solve all the problems. It could be a problem of different domains, different sectors, but one algorithm that can help us solve all the problems basically. That is the end objective of this workshop, right? Now let's come to autoencoders. So autoencoders, I won't get into the detail of it, but let's say what autoencoders do is they kind of, so neural networks are basically universal data approximators, right? So let's say if you give a sample of, let's say, 100 records, or let's say 100 million records to the neural network, they kind of, they build a function that could, approximate that data. What do I mean by approximate the data? So if for a particular given input, they can approximate or they can ideate what the output would be, right? For example, if let's say to us as humans, two numbers are given to us and told us to add, let's say 2 and 2, we are also in a way a universal approximation function, although we are very accurate in that. So if two inputs are given to us, let's say 2 and 2, and the task that is here to add those two numbers, we will quickly say 4, right? We will quickly say 4. And that is also what neural networks do. They kind of approximate the inputs, and they achieve, or they kind of duplicate the output from the inputs. How can they achieve the output? That's what they do. So in auto encoders, they kind of do this. They, from the given input, how can they achieve the output? Now, when it comes to anomaly detection in auto encoders, anomaly is usually a different point in a normal data. From a normal day, a different day is an anomaly, right? So what we do is, if let's say we segregate the data, and obviously autoencoders would need labeled data, that this is an anomaly and this is normal data. I hope everybody knows what is labeled data. So let's say if we want to build a machine learning algorithm which can tell us which is an anomaly and which is not, we had to teach that algorithm by giving some data, that this data is normal by labeling them as normal, and this data is anomalous by labeling them as anomalous, and then feeding into the model, and the model then trains on it, right? This thing is not applicable for clustering algorithms because these are unsupervised. They don't need the labels, but they can work just by grouping similar data together, right? And they might not know, they might have clubbed or grouped the anomalous data also, but this is how it works, right? So talking about supervised algorithm which need labels, autoencoders, when we feed the data which is, let's say, anomalous and non-anomalous, they would kind of try to estimate that all the data points which are there in anomalous, and whenever you give a normal data point or an anomalous data point, it will be able to segregate or classify between the two, that this point which is coming, whether it is anomalous or normal. Just as humans can understand the data which is coming, and an auto encoder would also be comfortable in assessing and understanding the data. Now the question is, if we can use the same auto encoder to different industries, different problems, different sectors of anomaly detection. So the answer is no. Each auto encoder would have to be trained on every different problem. So every problem would have a different data to it. So for example, let's say we are finding the anomaly in a in an e-commerce store, wherein what were the anomalous data. So let's say if on some day there was a very big hike of sales, that day is anomalous. It is an anomaly. Although it is good for the company, but from normal pattern, it is an anomaly. Now, if we are training a model on this data, that model or that trained model cannot be used on a different problem of time series. Let's say when we are predicting the temperature of tomorrow or like the next 10 days, the same trained model cannot be used for that, right? So all the auto encoders are awesome in what they do, but they need huge amounts of data, and they also needed to be trained again and again on every specific problem, and then they are very specific to the solutions. So one autoencoder trained on a particular thing can solve only that problem. We cannot ask that model to train or basically to solve a different problem. So that's the thing. Although they are awesome, but they also do have their limitations, right? Now, coming to the main point of this workshop, what I wanted to talk about is matrix profiles. What is matrix profile? So before starting the matrix profile, so far, any questions you guys have, any discussions you want to make? How can you predict then next anomaly? Okay, so interesting question. So First of all, anomaly does not have any pattern. If anomaly have pattern, then they are just normal, because anything that has a pattern is normal. Like imagine your life. You have a day-to-day pattern. You wake up a certain point of time, you do certain things, then you sleep. You have a pattern. Anything that has a pattern is not an anomaly, but normal data. Agreed. An anomaly is something that breaks that pattern. So basically, we cannot predict the anomaly, the next anomaly, but we can detect in the already existing data what are those anomalies. Make sense, Ali Minhaj? Okay, awesome. Any other questions you guys have? I think we have one question. Okay, that was one. Okay, great. All right. Any other questions? I think we have already discussed so many things. Any questions you guys have? If tornado destroys your house during the day, it's an anomaly. Exactly, exactly. A weird or and a very unfortunate example, but yes, that's true. What else? What else? What else can you ask me, guys? Okay, so let's get back. Or if you have any questions, I think we should probably wait for a couple of minutes, ask your doubt, discuss some things, and then move on. Because the next would be a little heavy. Okay, so anything detectable must be part of a pattern because it's happened before in order to be detected now. Yes, yes. So the thing is, anything. Let me read it again, probably because I don't want to give any confusing answers. Okay, so anything detectable must be a part of a pattern because it's happened before in order to be detected now. So see, anomaly might not have occurred before, but still it can be detected because it's a different from a normal pattern. So if there is something different from a normal pattern, it should be detectable and it should be an anomaly. Exactly. So if it's seasonal pattern, it's not an anomaly. It's predictable. Exactly. So if there is a pattern or maybe a correlation, it's detectable and it's not an anomaly. I mean, yeah, I'm trying to create a boundary what normal looks like. And but sometimes the thing is, the normal pattern is so random for the human eye at least that you cannot make out any pattern out of it. So for example, as I was talking about the e-commerce store wherein they were very high correlation, still you could make out certain things, right? One second, let me, I'm so sorry guys, let me bring my charger. Hi, can I get my charger? Charger. Okay, so let's say food company profit is high during festival, then it can be treated as an anomaly. Actually, yes. So the thing is, they do treat it as an anomaly sometimes. So for example, let's say in the COVID period. So let's say things were running normal, and then the COVID period happened, and suddenly, opposite to what everybody was assuming or predicting, the sales of e-commerce companies actually went very, very high, right? So in that case, they consider it as an anomaly actually, right? So in some cases, they do consider it as an anomaly, but usually if everything is going very well, so in sales in the seasonal festivals, they don't consider it as an anomaly. They rather try to absorb that kind of effect in the future season so that whenever that kind of festival comes again, they can maybe be ready for that kind of demand in the future. Coming to the next question, so the time period of the study or the time series determines if something is normal or anomaly. Exactly, that's a very good point actually. That considering the time of the time series, only by analyzing what kind of period we are discussing, then only we can determine whether it's an anomaly or not. Any good resource to further understand autoencoders and how they are used to detect anomalies? I would say a good resources of autoencoders you can find on. There are a lot of good medium blogs for autoencoders. I would say Black Friday is a good example of an outlier. It's a good outlier in such cases and must be take note of it when analyzing and reporting results. I think yes. If let's say Black Fridays, I think every year Black Friday sales happen every year, and the sale skyrocket every time, right? So if let's say we are pre-prepared for that kind of demand, and if we can maybe predict that kind of demand in the previously, it would be good for the company. So usually these kind of Black Fridays or festive seasons, all the companies who are trying to predict or basically analyze the kind of demand there would be in the coming times, they do encapsulate or they include these kind of peaks in their predicting models. But sometimes, for example, in the COVID time, I'm saying there was this was a very specific case wherein the prediction was something else and something else happened. So in that case, their usual model would fail and it might take negative or bad data as input. So that's why they consider that prediction as anomaly and don't consider it. I don't want to go into the details of it, but what I'm trying to say is, let's say if we feed an anomaly to the model, then it will be trained on bad data. And if you input bad data, you will get bad results. So usually all the people who basically train models on time series data sets, they first detect the anomalies, they remove those anomalies, and then take the data, train the model on that data, and get the prediction. So in some cases wherein we want to basically improve our model, and for instances, as I was talking about the COVID times, there was a huge increase in the demand, and this might, if we feed this data into the model, this might cause the model to learn bad data and cause bad results basically. So that's why we don't consider it and consider rather treat it as an outlier. I hope I have made things slightly clear and not confuse them rather. Okay, so we have more questions, I think. Okay, any good resource for further? Awesome. Okay. Um, isn't seasonality an anomaly with respect to other data? That's a very good question, I would say. So, isn't seasonality an anomaly with respect to other data? Um, so first of all, there could be multiple seasonalities in a data set. All right. So let's say let's study the traffic of a city for an entire year. All right. So there could be seasonality of a day. So every day same pattern. Like morning, whenever all the people go to the office, there is a rise in traffic. When they reach office, there is a slowdown in traffic, and when they come back to their homes, there is a rise in the traffic, and so on. So basically, every day there is the same pattern. So there is a seasonality of one day, basically. Agreed? Everybody agrees with me? So there is a repetition pattern of one day. Now, let's consider a pattern of 7 days. And obviously, you will agree with me, there is a repetition of every 7 days also. Because all the 5 days, there is this pattern, and then 2 days break, wherein there is very less traffic. And then again, for 5 days of work. So there is a seasonality of 7 days also. So there is a regular similarity of one day, regular seasonality. Then there is a seasonality of 7 days also. And then there is a seasonality, I would say, of I can I think there can be a seasonality of seasons also. So I mean, in some seasons there might be more traffic compared to other seasons. So that might also be a seasonality in a case, right? So first of all, when we talk about seasonalities, they can be multiple seasonalities in the data set. That is one thing. Now, can seasonality be considered as an anomaly? So the thing is, seasonality is something that happens again and again. And if something is happening again and again with a particular pattern, then it is the normal. It is not an anomaly. Right? Agreed. Okay. How can you predict the next anomaly? I guess this I answered. For a year, holidays are repeatable and creates annual seasonality. Yeah, so this is in case of e-commerce website, but the time series is applicable to basically a lot of other things as well. Just in case of traffic, I gave an example, right? Okay, so let's get back to the workshop, and let's, if you guys have any more questions, I can discuss, and we can discuss that later also. Let's get back to the workshop and continue what I actually wanted to discuss with you. So, matrix profile. Anybody so far who have heard of what is matrix profile? I just wanted to know. What, anybody who has maybe in the past gone through what matrix profile is? Okay, so I think this would be something new for everyone, right? Interesting. Awesome. 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 Okay. All right, guys. So let's start with matrix profile. What is matrix profile? So let's say we have a time series of length n equal to 13. So basically 13 points. Although I have never met with a time series which is so small, just 13 points. But let's take an example wherein we have a time series with length of n equal to 13. And here the objective is to how we can find a matrix profile of a time series pattern. So the objective is how we can find the matrix profile of a time series data set. All right. Now here we have any 13 data points, 0, 1, 3, 0, 1, 3, 2. These are just values. And let's say x-axis, we have the day, and on y-axis, we have these values, 0, 1, then 3, 2. Let me bring a laser pointer. Okay. Then 3, 2, 9, 1, 14, 15, right? So this is just a time series, random time series. Now, if I ask you, can you determine any patterns here, or are there any anomalies? So obviously, to the naked eye, we cannot see any patterns or any anomalies here, right? Because they are not really very evident, right? Okay, so now let's understand what is a subsequence. Subsequence is a small part of a big time series. Subsequence is a very small part or a small sample of a big time series. Here, we have a subsequence of 2 elements. We can also have a subsequence of 3, 4, or more elements, right? So what is a subsequence? Subsequence is basically a small part of a big time series. And it could be from 0 to, let's say, n number of elements, where n is less than the total number of elements in the time series, right? Okay. Awesome. All right. So here we have taken these two subsequences, the first two elements in one subsequence, right? And here these 2 points will be considered in one subsequence, right? Now the subsequences, as I was telling, could be of multiple lengths. It could be of 3, it could be of 4, it could be of 5, right? Now, how can we compare two subsequences? Let's say we have taken a subsequence of 4 elements, 0, 1, 3, 2. This is one subsequence, right? And this is another subsequence, which is 1, 2 to 10. Now, in the same data, we have 2 different subsequences, right? If we find the difference between these 2 subsequences using Euclidean distance. So anybody who doesn't remember Euclidean distance from high school, it was just the difference between 2 points. If we can measure the distance between 2 points in the form of a straight line, that is the Euclidean distance. And obviously this is the formula. So 1 minus 0 is basically this x1 minus this, let's say, y1, or x0. Then this y1 minus this y0, 2 minus 1. Then 2 minus 3, which is 2 minus 3. And then 2 minus 10, which is this 2 minus 10, right? And we're squaring this, and we are square root over this entire sum squares. This would give us the Euclidean distance between these 2 subsequences, right? Now let's visualize this. This is our first subsequence, as you can see, 0, 1, 3, 2. Now we slide the window to the next element, and now we get a new subsequence, which is, let's say, 1, 3, 2, 9. This is the next subsequences. If we slide it to one level next, right? Now, if we find the difference between these 2 consecutive subsequences, we will get some value x. All right. So as you can see here, this is one subsequence. All right. And if we find the difference between itself, the value would be 0. Agreed? You guys agree with me so far? that if we find the difference of this subsequence with itself, the value would be 0, right? Any questions for? For a Okay, sorry, I missed your question. So, which part do you want me to explain again? Okay, thank you, William, for agreeing with me. Bilal, anything that I can explain? Okay, awesome, awesome. All right. So I think we have an understanding and we are clear. All right. Okay, awesome. All right. So if we find the distance between this subsequence and itself, which is this subsequence, the distance would be 0, right? And then let's say we shift it to the next level and we find the difference between the next subsequence, which is this one. The value that we get is, let's say, 7.4. And let's say we keep sliding this and keep finding the distance between the subsequence, the next subsequence from this one. Then we get this and so far. So in this way, we, let's say, fill this, and this is all the distance profile that we get by finding the distance between this subsequence with every other possible subsequence that can be in this particular time series. Right? Now, next what we do is, we were considering the difference from this subsequence. Right? Now we will shift this to 1329. This will be our next subsequence, and we'll start finding the distance of every subsequence there. Right? So what we will get is some kind of this thing, a 2x2 matrix. So the first row is basically when we find out the distance of the first subsequence with every other subsequence. The second row we can find out when we find the distance of the second subsequence with every other subsequence, right? The third row we can find out by finding the distance of the third subsequence with every other subsequence. Agreed? You guys agree with me how we can find this 2D? Are all the profile differences compared to the first subsequence? So the first row here, in the first row of the entire 2D matrix that we will eventually get. Okay, awesome, Nishant. Similar to correlation matrix, I would say. Yeah, I guess yes, you can say that. Maybe. So I think any of us who couldn't understand this part, because this is slightly mathematical, and before moving forward, I would really want that I put my point forward and everybody understands this, and especially people in their undergrad, or let's say in their initial years of college. And what basis do we select the 4 elements of sequence? Very good question, Prateek. And let's hold on to that question before we move ahead. On what basis do we select this subsequence? It could be anything, right? It could be 2, 3, 4, or 5. But on what basis do we do that? Let's hold on to this question. Once let's complete the entire matrix profile thing, and let's then come to this question again. All right. But really good question. Thank you for asking me that. All right. Awesome. So this is the distance matrix profile that we get eventually. What we do is, from this 2D matrix that we get, we find the minimum distance from every row. We find the minimum distance that is there from every row, right? So here the minimum distance is 6.9. If I get back here, as you can see, apart from 0, apart from 0, this first 0, what is the minimum distance? It is 6.9, right? So from every row, we find the smallest distance from every row. So we have transformed this 2D distance matrix into this 6.9, 1.4. From the third row, this is 6.2, from basically so on and so forth. The minimum distance or value from every row apart from 0. And hence we get this, which is a new, I would say, time series. Starting from this time series of 13 elements, we get another one, right? And let's find out what use can we make of this particular time series that we have used. So we have input a particular time series, done some mathematical operations on top of that, and then transformed that particular input into a different output altogether. And now let's analyze how can this be beneficial or important to us, right? So let's come back to the impact of using this on time series or signal data. Now, one more thing I would like to add is signal data is also time series data. Signal data could be any data that is coming from signals. It could be temperature sensors, it could be ECG sensors, it could be our electrocardiogram, the ECG signals, or different sensors that we use for healthcare on our watch, smartwatches. There is also a signal, right? All these are time series signals. Now, so this is a simple, the red one is the actual data, right? This is just a normal data, and you see these three layers are anomaly, a difference in normal data. Then again, normal data, which is very erroneous, a lot of errors and a lot of instability in the data, and then some, what you can say is some difference in the normal pattern, right? If we plot a matrix profile of this normal data, this is what we get. Same error, same aberrations in the normal data, and then this curve here, this curve here. Now, the corresponding subsequence in the raw data at this location must have at least one similar. So basically the point I'm trying to make here is we have transformed this input data into a different input data, wherein the anomalies you will find at here, and it has now become more easy to find anomalies because this is more evident from this. And this can be used as a pre-processing step basically in every industry, and this is applicable to basically every data that is possible in time series. It could be signal data, it could be e-commerce data, it could be taxi data, it could be basically any data from any sector and any industry, and we can use matrix profile to that data as a pre-processing step to basically break down our complicated, or let's say very huge time series into easy, intuitive, understandable form. Let me see some more examples that you understand it better. Now let's take an example, a taxi example. Given a long time series, this is a very long time series. All right, where should you examine carefully? The problem is called attention prioritization. Where should you focus your attention on? Right. A group of Stanford is working on this. However, we can think of profiling as for free. So as you can see from this data, which is the red data, we have created this matrix profile, right? And if you look at this data, understanding this data is actually not that easy because it's just the same patterns everywhere, right? Just the same pattern. But if you consider the matrix profile, you will see that there is one clear anomaly here, which you can maybe understand also why this anomaly happened. Maybe a ride rush on certain days, certain very busy days, right? And then you can also say that the highest value corresponds to Thanksgiving, which is this one, right? Now, this data is more easy to understand and interpret compared to this data, right? And we can easily explain at different points wherever there is a pattern match, right? So, and if you notice, this particular seasonality is being repeating again and again. This, then this one, and then this one. This is repeating again and again. And now it has become clear to us that this seasonality is there. And in here, if you notice, you cannot really understand if there is any seasonality or not. But this becomes really intuitive to us. And for algorithm also to write on top of it, it becomes easy for any machine learning algorithm also that there is a seasonality here. So if we apply any of the time series model or any of the deep learning algorithm to the matrix profile, it becomes easy for them to train rather than this, because this is rather confusing. Do you guys agree with me so far? Okay, so what does this mean? Work if the time between values is not constant. Okay. So a question from EY, does this technique work if the time between values is not constant? So whenever we work in time series, there is this one, I would say, default assumption that every time series have constant intervals. So we would, if let's say we have a value at January, we have a value at February, and we don't have any values for the next 3 months, then it becomes really very difficult to handle such cases. So in this case, this is more like a pre-processing step for us data scientists. So what we do is we kind of explorate, or we kind of predict, or we kind of just fill in some values which we think would be the actual value of month March or month April or month June. If any of the values is missing between the constant intervals, we try to fill in those values, which is also known as missing value analysis step in a data science process, or as we say, a crisp DM process. So the entire pipeline of data science is known as the crisp DM process. And the first step, I would say, is missing value analysis, wherein we fill in the data wherever the data is missing so that we make constant intervals. And that is like a by default step. So having said that, the answer is, we, for every algorithm to work on and even to make sense out of it, to make it even sensible to humans or to the machine, we would need constant intervals. And only by that way we can basically that predict the graph, or the upward or the downward trend, basically, if we have regular interval of data. Coming to the next question, I can see this being somewhat similar to RMSE to magnify errors outliers. RMSE to magnify errors outliers. So RMSE is root mean square error, right? And we find the root mean square between actual and predicted data, right? Now, maybe I don't understand your question properly, but how can we use RMSE to maybe magnify the errors? Like, I am not making sense of this question actually. So that's why, if you can maybe clear this out. Meanwhile, any other questions do we have? Can we apply time series analysis in agriculture? I think you have to give me a use case. So if let's say we have to predict the crop yield of an area, we can. Let's say if we have to predict the yield every year, this looks like a pretty in-depth resource. Looks interesting. Anomaly detection with auto encoders. Yeah, I think this is good. On what basis do we select this question? Where are the questions going on? I'm not sure. So the question was that, how can we use on isn't seasonality anomaly with respect to the data, although the profile calculated by comparing. So can we apply time series analysis in agriculture? So I think yes, definitely we can. We just have to think about a specific problem that we have to solve in agriculture, right? Does this technique work with time? This I have answered. Okay. All right, I think I've answered all the questions. Apart from these, how can you predict the next anomaly? If we can predict, then it's not an anomaly. Awesome. All right. Do we have a Python library you recommend for matrix profile transformation? Yes, exactly. There is Stumpy. All right. So let me continue with my presentation, and then let's discuss all the questions that you have. Okay. Now, Italy power demand. So this is basically electrical consumption of a country, or of Italy, sorry. Right. And as you can see, this is the data. The red part is the data. Now, if you being human, or let's say, could any algorithm can actually understand this pattern? Do you even see any pattern? Like, we see that there is one drop here, then again there is a drop here, again there is a drop here. There might be some seasonality here, right? But we cannot be for sure, because there is so much of data and we cannot really analyze this, right? But if we decompose this into a matrix profile, this is what we get, the blue part of it, right? The clear peaks, as you can say, represent to particular days. These are clear peaks, absolutely clear peaks, and there is no doubt about them, right? And all these, by analyzing just matrix profile, we can be very sure that there is a peak here, this must represent something. And then we kind of reverse engineer which date it was, then what it might represent. So let's say this peak lies on 14 April, this represents Good Friday or Easter Day, that's it, right? So basically, understanding and decomposing any time series into matrix profile help us to understand that particular thing better. And if let's say you use this data, the blue data, the matrix profile, for building any model, it even becomes more simple and more intuitive for the models also, because the data is now more clean and more intuitive rather than this, right? Makes sense. So this is what I've introduced to you guys, is not an algorithm for prediction, but an algorithm as a pre-processing step. Whenever you get a time series data, if you apply matrix profile to it first, and then maybe use it for any of the people, any of the anomaly detection, or maybe forecasting, or maybe finding the seasonality, anything basically, this would rather be beneficial and helpful to us, and easy also, and very intuitive, right? In ECGs also. Now this is the ECG. Now unless and until we are a doctor, we cannot determine the difference between these normal and this slightly different thing here. Although this is very significant here, but in normal ECGs, I have seen a couple of normal ECGs. This is very significant. Sometimes it is not so significant. And if we have to, let's say, build an algorithm which can, from this data, detect if there is a problem in the ECG or not, it has to be very, very precise and exact, right? But if, let's say, we transform this input data into matrix profile, then this becomes very intuitive. And I would say basic algorithms can also classify and detect these kind of anomalies. If we first apply matrix profile on the time series, it becomes very easy. And we can even use easy algorithms, very simple algorithms, to determine the anomaly in this kind of data, in the electrocardiogram data, which is so critical to the hospitals and to the entire healthcare departments, right? Now, this is a very interesting example that I have in front of you. So these guys are actually analyzing the voice of a bird. So they are actually analyzing that, are there some patterns that the bird speak in? So let's say if there are some patterns that the bird speak in, maybe they are speaking some words which are understandable by other birds. So basically, let's say if they are repeating some words, maybe that is a particular word. So for example, I am repeating certain things again and again. For example, anomaly. So whenever I speak in anomaly, there is a sound wave. Now this sound wave will match with every other sound wave that I have spoken and taken the word anomaly, right? All the anomaly that I have spoken so far, every subsequence of that sound wave will match, right? And if that matches, maybe I'm repeating the same word again and again, right? Do you guys agree with me? So this was the experiment behind what they were trying to achieve, that they were trying to find out if birds also have a language that they speak, and if they have some similar intervals, they have some constant sound wave, basically similar sound waves at constant intervals of time, maybe they are having a conversation with each other, talking about the same thing, same context of. Interesting, right? And then what they find out was, this is the actual data, and then they converted into matrix profile. And so this is, I would say, not very clearly understandable by humans and not very intuitive. But if you notice here, there is a dip here, and the same dip can be observed here as well, which is represented by these green and blue portions. And this they were able to detect with the help of algorithms and some computers, right? And what they analyze is basically that while it is clear that this is time series is not random, this is not a random time series. So basically, they are not just producing any sounds. They do have some significance, or that there is a meaning behind whatever they are speaking, because there is a pattern in that, and this is not really random, right? We did not expect that the motives to be so well conserved. So by conserved, they mean basically so well replicated. So these patterns are so well replicated that they can be observed and can be understood. So there is evidence of vocabulary and maybe even a grammar with birds. Interesting, isn't it? Like who knew we could apply this to these kind of things, right? Okay. So yes, I have not answered that question of how we can choose the subsequence. That I'll answer. Uh, like after 5 minutes. All right. I could have used last month. I see. I like it. Yes, exactly. This is very interesting, right? Yeah, I'll answer that. No worries. So thanks for the link. You can select subsequence length to like grid search. You can exactly. So now answering that question of how we can select subsequences, basically that. So first of all, creating matrix profile is a very I would say a very heavy process in terms of uh, time and space. Maybe a curse word dip for the birds. Awesome. Okay, so time series is basically a very heavy algorithm, right? So, I mean, matrix profile is a very heavy algorithm because we have to find out the difference between every sequence with every other subsequence. So basically, it's a n square complexity. So if let's say you have a million elements and there is a subsequence of let's say three or a four, you'll have to have a million square complexity, which is like worse, right? So that's why the grid method that you are proposing is actually not that great because it basically first of all finding the matrix profile is entirely so difficult, so complicated process that it requires very high compute power. Then if let's say you are finding matrix profile for every particular subsequence and then analyzing which is the best for you, it would be a very heavy process, right? It would be a very complicated process. Do you guys agree with me or not? And usually I don't prefer that way because I usually work with millions or billions of data and it takes almost all the time to just find out what is the best subsequence that we can work for. Make sense? And let the cat into the duck. I could probably use this to determine the sound if you can means cat. Awesome. Yes. Maybe William. Maybe. Definitely we can. There is a lot of experimentation. So I was talking about, guys, let's come back to, I was talking about what kind of subsequence, what length can we decide that this should be the perfect length of the subsequence that we should move forward with. And there is one method, as somebody was suggesting here, is to find the grid. So what is grid? Basically that for every sequence, let's say for 3 elements, for 4 elements, for 5 elements, for 6 elements, we plot the data and we see basically for every subsequence, we find the matrix profile and we see for which matrix for which subsequence we are finding better patterns or better seasonality, and that there is a library which plots a grid for that, right? Using that grid we can analyze which is the best subsequence for this data. Now this length of sequence will differ for different data sets. Our duty is to find out which subsequence length is the best that will work for this data set, right? Now there is one method which I just said, finding basically finding the matrix profile for different subsequences and then understanding which is the best. But this is not very, I would say, very practical because it takes a lot of time. But what we rather do is we do random search rather than grid search. So I randomly select uh, one value which I intuitively feed. So let's say we have a million elements, right? I plot separate parts of that element and I see if I can observe any seasonality. And whatever the length of that seasonality is, I take the half of it. That's what my method, and it's been working so far so good because if let's say you take the half of it, when we find out the matrix profile, it will be successfully be able to plot that kind of pattern. What I'm saying to you guys would not be very intuitive and not very helpful because I'm just speaking out to you guys, but you have to practically experiment it. So take my word for it as of now that whenever you get a big time series data of let's say a million data points, plot some random samples of it and identify if you can intuitively feel a seasonality or not. If there is some seasonality, find out what is the length at which it is repeating, right? And then take the half of it as your subsequence length. I mean, that is, yes, that you can do benchmarking the model with the window sizes. That is one approach which you can use. But the one that I was talking about was slightly different. more experimental based, I would say. Anyways, there are methods which tell you which is the best subsequence length which you can use. Now, coming to questions, how do we choose threshold value in matrix profile to find anomaly? How do we choose a threshold value? Interesting question. I'll come back to that. Can we apply matrix profiling iteratively to get more insights? I think you won't find any more insights if you apply a matrix profile to a matrix profile because it's already simplified in a way. You will basically just get the same pattern in a way. Now, coming back to the question, which is how do we choose a threshold value in matrix profile to find an anomaly? Now, this is a very good question actually, and there are multiple ways how we can find that threshold value to find out the anomaly. Okay, so let me come back to my screen and show you some patterns. Okay, so let's say this was the data. The blue data is the our matrix profile, and you want to find out the anomalies in the data set, right? What could possibly you choose as a threshold value above which you will find an anomaly? How can we do that? So one method, as we discussed earlier, is finding the central tendencies. If we find the mean of this data, and then we plot 3 standard deviation above and 3 standard deviation below, anything which is above the 3 standard deviation we can take as an anomaly. That is one way. Second way is by the box plot method. If you guys know what box plot method is, and I think if you are from a data science background, a lot of you might know what a box plot method is. That is the second way. Now there are many other ways as well, right? So for example, I'll give you an example. So whatever I'll say now is basically not entitled to everyone, and if you don't, let's say, understand it, it's totally okay, it's totally fine. I'm just telling something which is not so complex but a little bit advanced, I would say, right? So let's say we have this data. I've already told you two methods how you can find or select the threshold value above which you can find an anomaly. One is finding the central tendencies. Second is the box plot method. Now, the third one is this data set that we have. All right. If you find the mean of it, now, mean of would lie somewhere between y is equal to somewhere 0.5 or 1, right? Because this on the y-axis we have scale of, on the y-axis we have scale of 0, 5, 0 to 5, and then 10, 15, 20, right? So I would say the mean would lie somewhere around 1, I would say, right? If let's say the mean of this data is 1, what I'll do is I will subtract the mean from this entire data set, right? Now this will be shifted towards the 0 line. There will be little aberrations above and below the 0 line, right? Little aberrations above and below the 0 line, and this would be very far ahead the 0 line, right? Now you can apply any of these methods which I already told you, which is median or box plot. All right. Any questions so far? I mean, any other questions? Because can we apply median profile to get more insights? I don't think that's a good idea, I guess. I don't think that is a good idea. Okay, I'll repeat that. I guess now it is clear. 1 second. So Ryan, I guess now it is clear, right? Grid search or random? Okay. All right. So let me explain it again, Shadab, for you specifically and specially. So one method is that we find the central tendencies, and the second method is find the box plot, right? So the other method which we can also use is that we subtract the mean from this entire data. Now this will shift below to the bottom because we have subtracted the middle line, right? And then you can apply any of these methods. So this is something which is very practical, I would say. You'll have to practically subtract it and analyze what I was trying to say here, and then maybe you will get it. some things that I'm saying from my experience, you can, yeah, okay. All right, guys. So I guess I'm, yeah, okay, awesome, Shadab. Awesome, everyone. I think I have answered almost all the questions. So I will stop my screen now. One second. Have I completed everything I wanted to? Okay, so there is one more example of seismology, which is earthquakes. And wherever there is something like this, we have this summary. So summary is basically that we can apply matrix profile to basically every industry in every sector, and this is more or less like a pre-processing step before we apply anything else, right? And I think, as per my experience, if we do very good pre-processing, we get very good results, even if we apply some simple algorithms later in the entire pipeline of data science, right? So pre-processing is a very important step. And for data science, I think matrix profile is a very unique and a very good step of analysis or breaking down complex things into simple. So I think that was it from my side. I would now stop the screen and I am, hi. So any questions that you guys have for me, any other questions which we have already discussed so far, you can ask me. Awesome. Okay, so I think I have probably answered all your questions, but it was lovely to see you guys and talk to you and maybe share my knowledge. Um, Thanks, William. Thanks a lot. You can find me on LinkedIn, I guess. I think it was mentioned in my on the website also, my LinkedIn bio. All right. Anyways, I think I had a great time with you guys, and looking forward to talk to you and interact with you. If you guys have any questions of or any discussions regarding basically anything, computer science, computer vision, deep learning, artificial intelligence. Thanks for sharing. Here is my link. Thank you, guys. I think Amelia can take it from now. I almost. Thanks, Michael. Thanks a lot, everyone. Thank you.